Tuesday, and it'll be the same format. So now that you're kind of used to it, just remember you have one next Tuesday. I'll send a big email either Friday or Monday. Friday I'm in the lab all day almost. So we'll see if I get it out Friday. But I'll send a big email with like, hey, here's your reminders for this coming next week. I really won't have any updates for lab stuff because that's just a continuation, right? We've had all the group A people coming in this week. I'm just going to send a reminder right now, a verbal reminder, because I still am getting some emails on it. But if you are in group A, you're detecting signs of a chemical change, and there are some pre-lab questions and some post-lab questions in that PDF when you download it from Blackboard in the labs folder. So I'm not going to mandate that you have those pre-lab questions done before you walk into lab. You just need to have them done before you open the online assignment and the post-lab questions. If you are doing the dry lab, group B people, you are just doing the conversions, density, specific heat dry lab. You're just working on that as you get time, okay? Just carve out a little time each day. I know I have not yet posted videos of the complex conversion problems. You guys are probably waiting for those. I'm going to by the end of the week, I promise. I did not get it done yesterday. So I will send that in my email when those are posted for you guys to look at. But I intentionally kind of want you to give your best shot at that dry lab first without a bunch of, supplemental videos. I'll post those and make those available for help. Okay, any other questions before we kind of move into lecture for today? We are starting chapter 2. So we're officially done with chapter 1. To kind of give you a kind of a helicopter overview of where we are. Exam 1 is going to cover chapters 1, 2, and 3. Okay, so we're a third of the way done. We'll spend 2 lecture days on chapter 2. So today and Tuesday. Then we'll finish chapter 2 and we'll move into chapter 3. We'll spend 2 days there. And if I'm looking at the syllabus, after that, we have exam 1. So it's kind of where we're at. All right, well, I'm going to share my screen and we will get into lecture for today. Okay. Let's turn this. So, new chapter, new hike. All right. I do promise, I think I've promised before, but I do promise we will eventually get to some Arkansas hikes. But I'm showing you all my favorite ones first. And all my favorite ones, unfortunately, actually I have one favorite that's in Arkansas, but most of my favorite hikes were not in Arkansas. So this is another one from our Grand Canyon trip. And this was early in the morning. You can probably tell. This was on the South Rim. The time of the year we went, only the South Rim is open. The North Rim is not open just because it's colder and you can tend to run into more ice and stuff on the trails. So we were on the South Rim, and the story behind this trail is the first day we went hiking in the Grand Canyon. So this was not the first day, but the first day we did go hiking. We ran into this couple that was older than us, like quite a bit older. I think they were in like their 60s, and they had hiked all the way down to the bottom of the Grand Canyon, and then they're hiking back up. And my husband and I were like, if they can do it, we can do it. And we're not like expert hikers here, but we do enjoy hiking a lot. So we were like, we're gonna. So we got up early in the morning. I didn't say feedback for me real quick. We got up super early in the morning, kind of like you did for this class, and we went and hiked this. So I'm still getting a little bit of feedback. Can y'all hear that? Are y'all hearing that too? Yeah. Somebody maybe. Okay. Hold on. Did that help? Is that better? Okay. So anyways, We hiked this. You can see the trail. I'll kind of point some of this out. Like here's one of the switchbacks. It's all the way down, those little red marks. And then the river is actually down in this kind of crevice. So you can't even really see the river from here. So we hiked all the way down to the river. There's actually a place you can stay down at the very bottom of the Grand Canyon. It's called Phantom Ranch, but you have to like reserve it probably years in advance. And then we hiked all the way back out. And it took all day, and I was very tired afterwards, but it was the most amazing hike ever. So if you want to hike the Grand Canyon, the South Kaibab Trail is a good one. All right, let's get into the lecture. So summary, we are going to get into talking about atoms today. Okay, so kind of a little bit of a intro to this. We've been talking about matter, and we've been talking about properties of matter. So we've been looking at matter at kind of like a macroscopic scale, matter as we can see it and touch it and measure it and observe it. Now we're going to talk about matter on a level that we cannot see with our human eye. We're going to talk about atoms. And so we're going to look at, there's 4 parts to Dalton's atomic theory. We're going to hit that. Then we're going to talk about, we're going to get inside of an atom, okay? And we're going to look at subatomic particles. So that might be somewhat of a review. You may have heard of subatomic particles, protons, neutrons, electrons. We're going to talk about how they're organized. We're going to talk about their purpose and their role. And then we're going to end with isotopes today, and their natural abundances and how to calculate the weight of an isotope. Okay, so here we go. Dalton's atomic theory. So before we talk about these pictures here, because there's a point to why we're going to play a little game. Dalton's atomic theory. So for a long time, scientists thought, before there were microscopes and things that allowed us to prove it, scientists speculated that all of matter was composed of small particles that made up everything, but that were so small, they were like invisible to us, okay? But yet they were so small, you could not break them apart. So scientists thought you could take a piece of matter and keep cutting it in half or breaking it apart until eventually you would get to some kind of particle that was so small you could not break it apart anymore. And they were right, okay? But it was just a long time after that that atoms were proved through the use of things like microscopes. So the first part of Dalton's atomic theory is that all matter is composed of tiny particles called atoms. And as we get ready to look at atoms, I wanted to play this game to illustrate this point. So I have 4 pictures here. You probably played this game before. Some people call it the close-up game, the zoom-in game, whatever. I want you to guess, and if you have, I don't know if I put this in y'all's lecture slides or not. Hopefully I didn't put the answers in there. If I did, don't look at them. I want you to guess, what are you looking at? Okay, so write down what is, and you can type it in the chat if you want. What is picture 1? What do y'all think? I'm going to write down what y'all's best guess is for picture 1. It's a close-up of what? Someone says mac and cheese, spaghetti. Any other guesses? When I first looked at it, I thought it looked like maybe a close-up of like honeycomb, kind of, maybe. Spaghetti, noodles, that's what everybody's saying. Okay, maybe this isn't as hard as I thought. So we're getting spaghetti, noodles. Okay, what do y'all think about 2? It's a close-up of what? A carrot, flower petal. Nobody thinks it's a close-up of the sun. Just kidding. Maybe I'm not. An orange, carrot. Okay, Tia's gonna back me on the sun. The most consistent thing, let's see, we've gotten flower petal twice, we've gotten carrot a couple times, so I'll write both of those. Maybe it's a carrot, and maybe it is flower petal. Okay, what do y'all think about picture number 3? Ashton says a sponge, Maddie says a sponge. Gum, okay. Cotton candy, could be. Okay, the most common answer we're getting here is a sponge. Okay. I like bubble gum though. That was my favorite guess actually. Number 4, what do y'all think number 4 is? Bone marrow, chocolate. Somebody else says chocolate. A lot of people say chocolate. Any other guesses? Candy of some kind. Okay, the most common guess here is chocolate. And you guys must have had the answers because you pretty much got them all right. Okay. So that's essentially what we're doing with matter today. We are taking it, we're going to zoom up really close. And if we zoom up enough, we're going to start to look at atoms. We're going to see atoms. Okay. This blank right here should just be the same as above. So I'm not going to fill that in because it's the same. All right. Good job. Okay, part number 2. So that's the first part of Dalton's atomic theory. I want you to know these 4 parts and be able to explain them or recount them on an exam if you need to. The second part is that atoms of a given element differ from the atoms of other elements. Okay, atoms of a given element differ from atoms of all other elements. Okay. How are they different? So that begs the question, how? Well, each element is characterized by the mass of its atoms, okay? So that's how they're different. They all have different masses, okay? Atoms of the same element have the same mass, different elements, different masses. So here's the illustration with this. Here's the example. We have Na and N. Do y'all know what's the difference between Na and N? Anybody could tell me? Yes, nitrogen and sodium. So Na is sodium. N is just nitrogen. And how are they different? Well, the numbers in red down here at the bottom that I'm going to underline, these are their masses, their overall masses. Okay, so when you account for all the subatomic particles that weigh something in an atom, and you write that down. Now they have different units, okay, units that we're not used to. So what are the units are not grams or kilograms here. Those would be massive, huge atoms, right? We are talking about really, really small units. Okay, for an atom to weigh 22, almost 23, the unit has to be incredibly small. There's no atom in the world that weighs 23 grams, right? So the units here are AMU. What does AMU stand for? They made it up just for atoms. It's very creative. Atomic mass units. Okay, that's what AMU is, atomic mass units. Those are the units for the mass of an atom, okay? So 22, almost 23 for sodium. An atom of nitrogen weighs 14. Okay, so if you come across 2 atoms and you don't know what they are, if you somehow have a way of acquiring the mass of that atom, you can then identify it, okay? Because we can identify them according to their masses. You're never going to find an atom of sodium that weighs the same as an atom of nitrogen, and then vice versa, okay? Anybody know what these small numbers up here represent? Usually in the top corner for the periodic table, you have another number that's different, and that is telling you the number of
Protons?
what? Yes, the number of protons, okay? It is known as the atomic number. We're going to get to that in a little bit. So don't get these numbers confused. The higher number is always the mass number, okay? Because you have more than just protons in an atom. All right, so that's 1 and 2. Part number 3 says compounds consist of atoms in specific ratios, okay? Only whole atoms can combine into compounds, all right? Compounds consist of atoms in very specific ratios. The key word there is ratios. I know it's not one we filled in, but that's important. You're never going to have a ratio with 0.5 something or 2/3 of something. They're always going to be whole atoms. You can't break an atom in half and join it to a compound. Now, granted, you have probably seen a chemical reaction written. I'll write you a very classic one. Sometimes people will write this for the formation of water. They'll write 2 hydrogens plus 1/2 oxygen makes water, okay? You know what? And here's what they're trying to say, 1 oxygen. So don't be confused by this 1/2 thing. You're never going, because if you take half of an oxygen molecule, you have just an oxygen atom, okay? So don't get confused by this. This is not telling us that we're breaking an oxygen atom in half. Here, we're breaking an oxygen molecule in half, all right? But this is not exactly what point number 3 is talking about, point number 3 is just talking about when you make a compound, the subscripts, okay, these numbers down here, the 2 and the implied 1, are never going to be a fraction, okay, because you have to have whole atoms in your compound. This right here that I boxed in front of the oxygen, we call this a coefficient. We'll get to this in chapter 5. All right, I'm talking specifically about your subscript numbers within a chemical formula for a compound. So unique substances are formed when elements join together in different combinations. So I want you to look at, hold on, I'm getting a question in the chat. I'll answer that in just a second. I want you to look at these 4 options. I'm going to launch a poll, and I want you to put your answer in on the poll, okay? So regarding number 3, portion number 3 of Dalton's atomic theory, there we go, launch poll. Okay, which of these compounds on the slide that you're looking at right now violates part 3 of Dalton's atomic theory? So put your answer in. I'm going to look at the chat for a second. So on a side note in the chat, yes, Gabrielle, there's times where to avoid writing fractions as a coefficient, if you just multiply everything by 2, like all your coefficients, then you end up with whole numbers for all your coefficients. And that's usually nicer. People ask you to avoid writing fractions in as coefficients as well. It's just some people want to break that rule. So a way to avoid writing in a 1/2 right here in front of that oxygen is to just multiply everything by 2. So you could write 4 here, and then if you multiply that by 2, you would have a 2 right there, right? And then you would just end up with 2 water molecules. All right, go ahead, get your answers in. We are almost all the way voted. A few people left. Which one of these compounds violates? Which one does not comply with the rule we just talked about? Okay, 4 more people. I'm going to end the poll in 5, 4, 3, 2, 1, end poll. Remember, I'm also asking that you all have your video on. Most of you do, but please join us. Okay, share results. All right, most of all, everybody got it right. 46 people, 84% of the class said D. Okay, so if you're looking at A, we see nice whole numbers, water, H2O, hydrogen peroxide, H2O2, and it does not matter if it's liquid or aqueous. It's kind of the same thing, actually. But what violates here is that we have a fraction written as the subscript for oxygen. You cannot take 1.5 oxygen atoms and combine it with 2 hydrogens, okay? So this is in violation. You should never have 3/2 or 1.5 written as a subscript, always whole numbers, okay? That's just what part 3 of Dalton's atomic theory is saying. Questions on that? All right, we're gonna do more polls in just a minute, in a little while.
Wait, I have a question though.
Yes.
So like, I don't know. So like, if it is like a 1/2 or like a 0.5, do we just, I don't know, round up, or like, can we even do that?
No, you should never see it. You just can't have a molecule or a compound that would have a 0.5. So if somebody's told you, oh, you have H2O 0.5, you'd say, no, you don't. That's just, it's wrong. You're not ever going to have that, because that's literally like someone telling you you have an atom that is oxygen, and you're splitting that atom in half, and you're taking half of that atom and putting it. You can't do that. Atoms do not split apart. Now, sure, if you read some scientific news, sometimes they'll talk about we split the atom or whatever. There are nuclear fusion experiments and things that we can do. We can join atoms together, but according to Dalton's atomic theory, when you make compounds, real compounds, you are going to join atoms in whole number ratios, okay? So you should never see a subscript with a 0.5 or a fraction or something. Does that help, Glenn?
Yes.
Great.
Yeah. All right, thank you.
Okay. Number 4, chemical reactions only change the way atoms are rearranged. Or I don't say rearranged, just arranged is what I meant to write. They only change the way atoms are arranged, okay? The way that they're joined together. They do not change the kind or the type of atom, okay? What that is saying is if I have atom X plus atom Y, when you join them or say I have a compound, YZ, okay? This is 2 different atoms in that compound, Y and Z. And if I do a reaction here, I might rearrange things. I might get XY plus Z. So I'm rearranging my atoms, but I'm never going to take atom X and make something totally new. I'm never going to make atom Z or V. All right. I'll never take X and make it a V. It's always going to be atom element X. Okay. So if I have a sodium atom, I can't just suddenly turn it into gold or oxygen or helium. All right. It's always going to be sodium. I might rearrange what I combine it with, but I'm never going to turn it into a totally different element. If that makes sense. Okay, so this will not happen. You can only rearrange them. So the point here, because we are constantly rearranging, think about how many chemical reactions happen every day. Just maybe even in your body, okay? Countless, more than a billion. I mean, it's uncountable how many chemical reactions are happening all the time, how much atoms are rearranging, okay? Now move outside the human body. Think about the atmosphere. Think about the sum total of all the human bodies on planet Earth. Think about things that our people are doing in medicine and science. Think about how many chemical reactions are happening all the time. Think about how things decompose in nature. That's a chemical reaction as things decompose. So constantly in our universe from day one, whenever it's created, we have a set number of atoms, right? And today now, those have just been rearranging and rearranging. They've just been recycled, okay? So this next slide, you're probably not gonna think it's funny. I always think it's funny. Atoms are recycled. That means that dead armadillo on the side of the road, the atoms that compose that. What is that armadillo composed of? It's composed of what we're composed of: carbon, hydrogen, oxygen, sulfur, sodium, okay? The atoms and the elements in that are going to eventually make it into our food, right? Because we just recycle all of those things. As it decomposes, it's going to be used as fertilizer. It's going to grow plants. We're going to harvest those plants. We're going to cook with those plants, okay? So if you zoom in on every sandwich you eat and every piece of food you eat, you'll see it's always made from 100% recycled atoms. So you're way more sustainable than you think you are. Nobody's laughing. Nobody ever thinks this is funny. I always think it's funny. Okay, let's go over some review poll questions. I want to make sure you kind of understand before we jump into the next thing what we just talked about. So these are going to talk about Dalton's atomic theory as a whole. So let me launch the first one. All right, I think there's two questions here. Read them carefully. First one is, which of these statements are consistent with Dalton's atomic theory? And I don't know how it's going to let you select answers. I don't know if it only lets you select one or if you can select more than one. There might be, I need to read the answers closely. If you see one that's, or more than one answer that's correct, and you can only select one, don't worry, you're not graded on these, but just select at least one that you know is correct. Okay, if that makes sense. So which one of these statements, there might be more than one, are consistent with Dalton's atomic theory? Does it let you select more than one? Or can you only select one? Yeah, I think you can probably only select one. Yeah, okay. That's my feedback to Zoom. They need to enhance their poll features. I'm very limited on what I can create. And then the next question, I see some people already getting down to question 2, is you're picking which one is not consistent. Okay, so make sure you're paying attention to that. The first question, which one is consistent? So which one would be true according to Dalton's atomic theory? The second question, which one's false? Okay, we're about 75% of the way there. We've got about 10 people left to get your answers in. We'll go over these and then we're going to jump into the next thing. All right, 3, 4 more people. I'm going to give you 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, end poll. Okay, let me share results. So for question number 1, the most commonly, there were 2 that were almost neck and neck, but the most commonly picked answer is the one statement that is consistent with Dalton's atomic theory was that third choice. So let's read through them. The first choice says sulfur and oxygen atoms have the same mass. That is not consistent with Dalton's atomic theory. Why? Right here. Rule number 2, that all atoms of a given element are different according to their masses. So sulfur and oxygen are 2 different elements, so they have to have 2 different masses. Okay, number 2, all cobalt atoms are identical. Okay, that is true. And this is why I wanted you to be able to pick more than one answer. Okay, so number 2 is also correct. All right, so just because it wasn't the most commonly picked answer, make a note for yourself if you need to. That second choice is also correct. If they're cobalt atoms, they're all identical. They're going to have the same mass. Okay, so that's enough to say they're identical. Now, some of you might be like, yeah, but what about isotopes? Okay, well, we haven't gotten to isotopes yet. So according to you, they're all identical. All right. Number 3, potassium and chlorine atoms combine in a 1-to-1 ratio to form potassium chloride. All right. That is true. The key thing there is it's a 1-to-1 ratio. So you're not splitting atoms in half. You have nice whole numbers in your ratio. So that could totally be plausible. Okay, the last one, lead atoms can be converted into gold. We wish, right? Somebody should have figured that out a long time ago. We'd all be rich. No, they cannot be. Okay, lead is just lead. All right, number 2. So which statements are not consistent? Essentially, you can say which ones are false. Okay, not consistent with Dalton's atomic theory. All carbon atoms are identical. Okay, that one's true. So that's not the answer we're looking for. We're looking for the ones that are not true. Okay, number 2, an oxygen atom. Sorry, I just saw a chat. Yes, there is tutoring. I'll get to SI in just a second. Let me finish this poll question real quick, Bailey. Number 2, an oxygen atom. Oxygen atom combines with 1.5 hydrogen atoms to form a water molecule. No, that's kind of the example we went over, right? So we cannot have 1.5 atoms. They have to be whole numbers. Third choice. So everybody picked that one. That's great. Good. Or most everybody. 2 oxygen atoms combine with a carbon atom to form carbon dioxide molecule. Yes. Carbon dioxide, CO2. So what that says is 2 oxygen atoms combine with 1. There's 1 carbon atom here to give you CO2. And then, okay, I'll go over it. Last one, the formation of a compound involves the destruction of one or more atoms. No, we do not create new atoms. We do not destroy atoms. We just have the same number of atoms that we've had, okay? So to go back to this first, I'm getting a question about the first poll question, all right, in the chat. Confused about answer 3 on the first question. Okay, it says potassium and chlorine atoms combine in a 1-to-1 ratio to form potassium chloride. So potassium is K. If you look at the periodic table, that's potassium. Chlorine is Cl. All right, all this is saying is if we're going to make potassium chloride, which is a compound, we're going to have 1 atom of K, 1 atom of Cl. So we get a compound that looks like that, KCl. That's what it means when combined in a 1-to-1 ratio. 1 atom potassium, 1 atom chlorine, you get potassium chloride. You don't have to write any of the ones in because we rewrite the letters and that indicates there's 1 of each atom. All right. So that complies with rule number 3 because we have a specific ratio and these are whole atoms. Okay. Does that answer your question, Bailey? Oh, no. 44% means 44% of the class picked that answer. Okay. Yeah, these percentages on the side just tell you how many people from the population of the class, the audience, picked that answer. Okay. All right. Any other questions? All great questions. In the chat, off topic, but do we have to have goggles for lab next week? Yes, you do. Okay, if you are coming to campus, you have to have your goggles. Okay, I always keep a spare 1 or 2 extra pairs just in case, but don't count on me having that for everybody. All right, let's get into the structure about it. Any hanging questions on Dalton's atomic theory? If I ask you, what are the 4 parts of Dalton's atomic theory? Or what is which example complies with like a similar question in the poll on the exam? If I ask you a question like that, do you feel comfortable and confident with stuff like that? Okay. All right, atomic structure. So now we're going to look at an atom, okay? So how does an atom look? Atoms are really, really, really small. How small are they? Well, if you look at this figure right here, the volume occupied by the negatively charged electrons. So this is essentially the diameter of an atom, okay? From here to here, that just an average diameter. Look at this, 10 to the minus 10. What does that M stand for? M stands for, what unit is that?
Meter?
Meter, okay? 10 to the minus 10 meters, okay? Now remember that 10 to the 10 to the 9 nanometers are in 1 meter, right? That's a billion nanometers in a meter. So saying we have 10 to the minus 10 meters, that's smaller than a nanometer, okay? Just to give you a little perspective, this is smaller than a nanometer, all right? It's really incredibly small. So that's roughly the diameter. That's how we mark the size of an atom, looking at the diameter of what we call, what is this space that's marked off right here? That is called the electron cloud, okay? If you read up here, this is the volume occupied by the negatively charged electrons. So we call it the electron cloud. So you can't see it. In fact, electrons are like too small to even see. But if we could draw them in, we have electrons zooming around the atom in this cloud. Okay, and we must have electrons on this very outer edge whirling around to say that's the maximum size of that electron cloud. Okay, now if we take this center dot right here and zoom in on it, I'm going to slide over, we call this the nucleus. Okay, that's the nucleus. And you can see we have some different things in here. So we've got different arrows pointing to stuff. First off, the size, if we're looking at the diameter of the nucleus, is probably approximately 10 to the minus 15. Holy smokes, that's incredibly small. 10 to the minus 15 meters. It's so small I can't even comprehend. If I had to write this out, it'd be like 15 zeros. Okay, I don't want to write out all those zeros, but you get my point. It's really, really small. What's in the nucleus? We see we have protons in the nucleus. That's pointing to one of these spheres, the red ones. And we have something called neutrons, okay? Now, if you read in parentheses, protons, they have a positive charge. So you could draw a plus sign by the proton to remind you these carry charge. So some of these subatomic particles carry charge. Neutrons, no charge. They do not carry any sort of electronic charge. If you notice when I wrote in electrons over here, I put a little minus sign by the E. Okay, E stands for electron, and we put a minus sign because they're negatively charged. Okay, so we're actually going to fill all this in down on this table right here. So first off, you've got the name of your subatomic particle. What's the symbol for it? Well, we abbreviate these things just with their first letter. So P for proton, N for neutron, and we do an E, we include the minus sign for the E. So it's E minus. We don't have to write the charge on the P and the N. Obviously, N doesn't have a charge, but we do include the charge in the abbreviation or the symbol for an electron. Okay, how much do these things weigh? Well, if we're looking at grams, it depends what units you're talking about, remember. In units of grams, I mean, the exponents here are just ridiculous, okay? So a proton is 1.673 times 10 to the minus 24, okay? My mind doesn't even, I can't even comprehend how small that is. Look, a neutron's about the same, 1.675 times 10 to the minus 24. And remember, it's talking about grams, okay? So if a dollar bill, remember that a dollar bill is 1 gram. So a $1 bill equals 1 gram. We're talking about 10 to the minus 24 grams. Okay, an electron is 9.11 times 10 to the minus 28. Okay, that's even more ridiculous, okay? So because these numbers are so astronomically small, we don't talk about them in terms of their grams. All right, it's amazing that we even have instruments and tools to measure these things, but we talk about them in terms of their AMUs. Anybody remember what AMU stands for? It's a different unit just for atoms because it's very,
Atomic mass unit.
Yep, atomic mass unit. So we made these to be nice round numbers. Essentially, I don't know what scientists got together and I don't know how they defined it, but they said on the scale of AMU, a proton weighs 1. And I'm very thankful they chose 1. A neutron, look how similar the masses are for a proton and a neutron. So therefore we said on atomic mass units, a neutron also weighs 1. And because an electron, if you look at the grams, the units on grams, the difference in the weight of an electron is different over an order of 1,000. Okay, so because they're that different, like an electron weighs almost 1,000 less than a neutron or a proton, we said an electron is going to weigh 0 atomic mass units. Question from the chat. Once we destroy an atom or atomic energy, do we ever get that atom back since we recycle them? Here's the deal. When you get into the world of nuclear energy, nuclear reactions, you guys have probably driven by a nuclear reactor on the interstate or something. You see the big smokestacks. We do use nuclear reactions for energy and for other reasons. So we can nuclear react things. We can, we have certain unstable atoms that decompose, okay? But we always use those subatomic particles will either join up with other atoms or they don't just go away, okay? We can't just make protons and neutrons disappear, okay? So even if an atom does decompose, Bailey, to answer your question, and you essentially call that destroying an atom, we can't just put that atom back together, okay? Easily, at least. And so they would join up with those subatomic particles would join up with other atoms, okay? That's probably the simplest way I can answer that. There's a lot more science behind that question, Bailey, but that's the simplest way I could put it to you. Does that help? Okay, good. All right, lastly, let's talk about the charge of these subatomic particles. We said a proton is plus charge, a neutron is no charge, an electron is negative charge. Okay, now how much are we talking? We're just talking a +1, a 0, and a -1. Okay, but just writing the plus and the minus is indicative that there's a single plus charge and a single minus charge on any proton or electron. All right, the last thing, so this table is kind of a summary of what we just said. Notice that the mass here for protons and electrons, like I did give you some decimals, but if I ask you on an exam, unless I specifically give you like a multiple choice question with this exact number, you can just always tell me a proton weighs 1 AMU and a neutron weighs 1 AMU. Okay, don't worry about memorizing those decimals. All right, what about the role? Why are these things in an atom? What do they do? They have roles. There's a purpose that they're there. Electrons are responsible for the chemistry. Okay, and another good word for chemistry is behavior. All right, so the electrons control how an atom behaves or interacts with other atoms, and we call that the chemistry of an atom. Okay, is it reactive? Is it not reactive? You guys probably recognize this picture down here. What is this?
Like an atomic bomb or some sort?
Yeah, atomic bomb, okay? Hydrogen bomb. Did you know an atomic bomb is a hydrogen bomb? Just hydrogen in there? Isn't that crazy? Hydrogen is the smallest element. So why the smallest element? How are we getting an explosion this big, okay? It's all due to the electrons, okay? Electrons, we'll find out later, electrons can jump between atoms, all right? They can be traded. We'll get to that later, but electrons are responsible for the chemistry, and sometimes the chemistry can be very, very big, right? Okay, protons. What's the role of a proton? They identify, I'm going to write ID, okay? They identify the atom. That is the identity of the atom. So if you have an atom and you want to know what atom is this, what element is it? If you can identify the number of protons, then you've identified that atom. Okay, a carbon has always 6 protons. A hydrogen always has 1 proton. The moment the number of protons changes, you no longer have that element. Okay, it's a different element. And they also account for the mass. They make up the mass of atoms. Okay, I should say they contribute to the mass of an atom, right? They weigh something. Electrons don't contribute to the mass of an atom because essentially they don't weigh anything. And then lastly, neutrons. What's the role of a neutron? Well, they contribute to the mass, right? They weigh something. They're also there to help hold the nucleus together. So we'll just say they are the nuclear glue. That's an N and a U, nuclear glue. Okay, and changes with neutrons are how we get isotopes. So in parentheses down here, I'm going to put they're also responsible for why we get isotopes. And I know we haven't even talked about what that is, but you'll understand by the end of the day. Okay.
Wait, what's that say? Like the last one, neurons or neutrons?
Neutrons, yeah. So contribute to the mass. They are the nuclear glue, and they make up what we call isotopes.
Oh.
They're how we get isotopes. Changes with neutrons are how we get isotopes. Okay. Any other questions on that? So if I gave you a table like this and said fill in all the blanks, hopefully you could do that. Okay, you could, or if I just ask you why are electrons important in an atom? Why are protons important? You could tell me why. I put this link on here. We're not actually going to take the time to watch it today. In previous semesters, I would always show this. It's like a 2 or 3 minute video. I like it because it just is a different way for you to kind of go through the same material I just talked about. It's a fun video. It's an old school TV show. And on it, they talk about how atoms are arranged. Okay, it's kind of funny. So if you want to go check that out, just throw that link in and enjoy that video. But let's do another poll. I just want to see, is everybody with me on understanding the different portions of an atom? So let's look at this one. Which statements about subatomic particles are true? Okay, this one is a multiple choice question. Does it let you select more than one, or can you still only select one?
You can select more than one.
You can? There I was hating on Zoom earlier. They let me do what I want. Okay, I tried. So they tell you can select a single choice or a multiple choice. So I'll know from now on if I want you to select more than one answer, I can give you multiple choice. Okay, so select all that are true. I'll be honest, that's been my biggest like struggle or difficulty with teaching online chemistry is making sure things appear to my students the way I want them to. Because I can write a whole exam and know how I want it to be answered, but sometimes the way it appears to you guys, I have to always double check that. So. All right, I'm going to give you just a few more seconds. So go ahead and get your answers in if you can. We'll go over this. All right, 5 more seconds. 5, 4, 3, 2, 1. 94% voted. Anybody else? Get your answers in. All right, we're going to end the poll. Share the results. Okay. So you were trying to select statements that are true regarding subatomic particles. So let's read them. First one, if an atom has an equal number of protons and electrons, it will be charge neutral. Okay, so that's not a phrase that I've used, charge neutral. What does that mean? But most all of you picked it, and indeed it is true, okay? If an atom, any given atom, we'll say atom X, has 10 protons, and these are, so that's like saying it's got plus 10 charges, okay, 10 plus charges. So total magnitude of positive charge is a plus 10. And then it also has 10 electrons, and the total magnitude of negative charge is a minus 10, okay, because each of those is a minus 1, and you got 10 of each. So that adds up to 0, which is, yes, charge neutral. And I didn't tell you this, but you should always know, an atom in its natural state, as you look at it on the periodic table, or if you go out into nature and you find that atom will always have the same number of protons and electrons, okay? Chapter 3, we're going to break this rule. We're going to look at something called ions. But for now, atoms in their natural state, if it's not reacted with anything, they have the same number of electrons and protons always. So they will always be charge neutral. All right, next one. Electrons are attracted to protons. Okay, 27 out of the 54 people who voted picked this one. That is true, okay? You know, opposites attract, okay? So there definitely is some attraction here. Protons and electrons are attracted to one another. So that one's also true. So the first two choices are true. Electrons are much lighter than neutrons, okay? Well, if you look up, you might be thinking, well, if you're just talking about their AMUs, there's really not that much different. It's a 1 and a 0. But if you look at their mass in grams, it was different over an order of 1,000. Okay, so yes, that's enough to say electrons are much lighter relatively compared to neutrons. Okay, protons have twice the mass of neutrons. That one is not true. So you should have selected every answer here except for the last one. Okay, protons and neutrons weigh, their weights are almost identical on atomic mass units or even grams. Okay, so questions there. All right, well, I'm gonna close that down. And we are gonna move into isotopes, okay? We're gonna talk about these two letters, A and V, and then we'll look at the natural abundance of different isotopes. So first off, what is an isotope? Actually, before we even get to that, why should you care about isotopes? Anybody have a thought on this without looking at your following slides? Anybody can tell me why isotopes are important? They're important for many reasons, but if you give me one example. Anybody ever heard anything about isotopes before? I know some of you took social studies or a history class or a science class back in like middle school or junior high. Anybody ever heard of carbon-13? Carbon-14? Okay, radioactive dating. Anybody ever heard of that? Like, how do we date fossils? Okay, we use isotopes of carbon. Okay, so that's one reason. I'm sorry, I won't say who, but somebody just goes, the Isotopes are a baseball team on The Simpsons. That's great. Couldn't tell you the last time I watched The Simpsons. Are The Simpsons still doing good? It's good to know. All right, here's rule number one, or I should say reason number one, why why isotopes are important. Energy, okay? Isotopes have the potential to release or create really, really large amounts of energy. So nuclear fusion, that's a very fancy term of hydrogen isotopes, produces large quantities of energy. And I've shown you a picture of that here. So the H's represent we're dealing with hydrogen isotopes, the 2 and the 3 right there tell us that they're isotopes of hydrogen. Okay, usually hydrogen would just be represented with a 1. Okay, it's just got 1 proton and that's it. Okay, this 2 right here, these numbers on the top, can I go back up a little? Yes. These numbers on the top that I've circled, this 2 and there's 3, they are the total mass of that isotope. So hydrogen just has 1 proton. That's what makes it hydrogen. So if there's a number up here bigger than 1, this 2 and this 3, that indicates we've got now some neutrons in the atom, okay? And a varying number of neutrons, that's what an isotope is. It's an atom with a varying number of neutrons. We're going to define that in a couple slides, so don't worry about writing all that down right now. But here we have 1 proton in this hydrogen isotope, and we have 1 neutron. And then over here, we have 1 proton, because that's what makes it hydrogen. So we must have 2 neutrons if the total mass is 3. You see how that adds up to 3? You see how this adds up to 2? If we're adding them. Okay. So when you fuse, okay, fusion, what does the word fusion mean? If I'm going to fuse 2 things together, I'm forcing them together. Sorry, I'm looking at the chat. Can you post something that points out what it means when numbers are around, so it is all in one place? Bailey, we're going to get to that. We actually have some slides coming up that are going to talk about what numbers mean what in one places. So if you still have a question on that by the end of today, I can do some more, but I think that question will get answered. All right, so if we fuse these hydrogen isotopes, all right, notice the gray ones would be the neutrons. So I'm going to put an N on those, and the orange one would be the proton. All right, in case you're wondering. If we fuse those together, they're going to rearrange the neutrons and the protons. We're going to get a lone neutron just floating off to somewhere else. And we're going to get a helium atom, an atom of helium. All right, and then notice what we get, 14.1 MeV, 3.5 MeV. What do these letters mean? These are units, by the way. They are mega electron volts. All right, now you do not have to know what an electron volt is. It's just a quantity of energy. All right, and mega is even bigger than a kilo. Okay, so that's a large amount of energy. Kilo is really big. It's 1,000 times bigger than the base unit. Mega is even bigger. All right. So the point I just wanted to make here is that isotopes are important because they provide energy. All right. Another reason that isotopes are important are for medical purposes. Okay, so just they're important in medicine. I'm just going to give you one example of why they're important. There's more than this. Some isotopes are unstable. Okay, decomposition. What is it? What does that term mean? Decomposition. Anybody know?
Breakdown.
The breakdown. You can think of a landfill where things are decomposing. So the breakdown of these unstable isotopes releases radioactive energy, and we can harness that or use that to kill cancer cells. All right. So here's an example with thyroid cancer. I'm just going to read this. Iodine therapy. So we're using iodine isotopes, and here's the isotope of iodine that we're using. I'll zoom out in a second. It's iodine 131, all right? Iodine 131 is an isotope that specifically targets the thyroid. All iodine targets your thyroid, but it's going to go to your thyroid and has very little effect on other parts of the body, okay? Because our thyroid is it's gonna absorb all the iodine that we feed our body, all right? So please don't deprive your body of iodine. Make sure in your diet that you're taking in good amounts of iodine. You can look up what sources of food are rich in iodine because your thyroid needs it. And if you starve your body of iodine, that's where you run into issues. You might have heard of people, you might have people in your family you know that have had trouble with their thyroid. It could be because they had a deficiency in iodine, all right? But when you do have issues with thyroid, if you have cancer cells in your thyroid, we could give it this radioactive isotope. So it's an unstable isotope. If it's radioactive, it's unstable and it can decompose. And here's what's going to happen. We're going to follow these steps through 1, 2, 3, 4. So the first thing, radioactive iodine is ingested in a drink or capsules. Radioactive iodine molecules are absorbed through the walls of the digestive tract into the bloodstream. Sounds scary, I know, but they're going to go to your thyroid. Okay, so we're going to ingest them. They're going to all go right up here. Your thyroid is at the base of your neck. So your thyroid gland needs iodine to work and absorbs most of the radioactive iodine. Okay. Hopefully that's like 99.99% most, because we don't want radioactive isotope other places in our body. And then the radiation is going to happen. So we have these cells here. If a cell absorbs that radioactive iodine, then that cell, what they're trying to show you is it's going to destroy this cell. Okay. It destroys cancerous and normal cells, okay? So that's the downside. There's always a cost-benefit analysis with cancer treatments, right? Sometimes we kill the good cells along with the bad cell, but that's the price we have to pay for killing the bad cell, okay? By the way, if you know somebody who receives radioactive therapy, health professionals are supposed to do a good job of instructing them on how to safely isolate themselves sometimes from other people, because that radiation can emit from your body. You don't feel it necessarily, you don't see it obviously, but you don't want to put anybody else, expose them to any sort of harmful radiation. So you have to take proper safety measures for any patients who are receiving a radioactive therapy. Okay, any questions on how isotopes are important? Again, there's way more reasons and purposes and uses for isotopes, but that's just 2 examples. All right, now we're going to pause on isotopes for just a second. I want to explain 2 properties or 2 things about atoms. Okay, the first one is called the atomic number of the atom. So we assign an atomic number to every atom, and we abbreviate this number with a Z. Okay, I don't know why they picked Z and not A. They just did. Z is the atomic number. Okay. And this is the number of protons in an atom. And remember, it's the protons that identify the atom. So this is the identity of the atom. All right. This figure right here on the left is just from the slides from earlier. So for example, carbon always has 6 protons. If you look at the periodic table, you will usually see the atomic number, which is Z, listed above the symbol for the element, or sometimes it might be up here in the corner. Okay, like we saw earlier with the sodium and the nitrogen slide. All right, so that's atomic number, just the number of protons. Another abbreviation for all these different numbers is mass number. Okay, and this is where it gets comical. Guess what letter they picked to represent mass number? A. How convenient. You're going to see A and you're going to be tempted to think, oh, that's the atomic number, because that makes sense to pick A for atomic number. But A is mass number, okay? And this is the sum of the protons and neutrons in an atom. Okay, so atomic number is Z, mass number is A. Atomic number is just the number of protons, but the mass number is the number of protons and neutrons. So guess which one will probably usually always be bigger? The atomic number or the mass number?
Mass number?
Mass number, because you have more things you're adding up.
Yeah, could you go back up like to the first one? It said the number is 6. Okay, that's just an example.
Uh-huh. Good.
Mm.
All right, y'all good? All right. One thing about neutrons. Protons, I mentioned this, but protons require neutrons in the nucleus to buffer positive charge. What happens, have you ever played with magnets before and you orient like the positive ends towards each other? Okay, they repulse one another. Okay, when you bring things that are positively charged close to one another, okay, they're going to repulse. And think about a nucleus of an atom. Let's look at this. All these red spheres are positively charged, and how are we shoving them together? Well, that's where neutrons come in, is they help buffer all that positive repulsion, and they allow the protons to stay packed together in the nucleus. Okay, now that we understand mass number and atomic number, let's go back to isotopes. Okay. Let's look at copper. Okay, copper is a transition metal on the periodic table. We abbreviate it Cu. Copper, they have found copper can be stable with different numbers of neutrons. What? How can this be? 34 neutrons or 36 neutrons packed into the nucleus of copper. And it's stable with different numbers. Okay. And if we're going to define now Z and A. Remember, Z is I'm just going to zoom in real quick and then I'll zoom back out. Z is the atomic number. Okay, it's the number of protons. A is the mass number. Okay, so let's define Z and A for each of these 2. Okay, well, to do that, if you have a periodic table, flip to that or look one up really quick. I thought this periodic table would be nice, but the resolution is awful. Look at this. When I try to zoom in on copper, can you even tell? This is a 29, but look, it's super blurry. So anyways, we're going to take that piece of information what does that 29 mean? Is that Z or is that A?
Z.
Yes. Okay, so Z for both of these copper atoms is going to be 29. A, though, will be different. Why? Because we have different numbers of neutrons. So how do we calculate A? A is equal to the atomic number, or the number of protons, plus the number of neutrons. So we'll do 29 plus 34 for one copper. A for the other one will be 29 plus 36. Okay, you should get 63 and 65. So when we're talking about isotopes, and in fact, I'm going to define what an isotope is. Now that we've looked at this example, now that we've talked about mass and atomic numbers, let's define what an isotope is. Am I good to scroll down? If I need to go back up, just tell me. So here's what an isotope is. Copper 63 and copper 65 are known as copper isotopes. Okay, why? Both are copper because they have 29 protons. Okay, but they are isotopes because they differ from each other in the number of neutrons. So an isotope is an atom with a varying number of neutrons. Okay, what is an isotope? It's an atom with a varying number of neutrons, just like you saw in the example with the copper, with the 34 neutrons and the 36 neutrons. They're both copper. And as a review, atomic mass is the number of protons only. Atomic mass. That's incorrect. That should be down here on Z. We talked about Z first earlier, so I thought we were doing that again here. That is the atomic number of protons. Atomic mass is the number of protons plus the number of neutrons, or you could just write P plus N. And then Bailey, here's what I was talking about. This shows you how to order and arrange all these numbers when you're writing the symbol for an element. We always put the mass number on top. Okay, so this 3, this is hydrogen, by the way. This is symbol of the element. We're talking about hydrogen. And the 3 on top, on the left side right there, is the mass number. We always put it on top. The number on bottom, the 1, is the atomic number, and that indicates the number of protons. Okay. Questions so far on isotopes? So could you define an isotope? If I told you you have iodine 131, could you tell me, if I gave you a periodic table, how many protons, how many neutrons are in iodine? Could you tell me that? Could you look at a periodic table, get the atomic number, subtract the 2, find the difference? Could you do that? In fact, let's do that. I have iodine 131. I want to know how many neutrons are in iodine 131. I'm going to go back up to my terrible periodic table. Okay, I'm gonna zoom in on iodine. I can't believe how bad this is. Right here. You can't even read that, but it should be 50. I can't even tell if it's a 55 or a 53.
53.
Thank you. So this number down here should be a 53. So could somebody tell me how many neutrons are in iodine? Sorry, I was reading the chat.
78.
78 is what we're getting. How did you get 78?
Subtracted 53 from 131.
Yes, 131 minus 53, okay? Because this is protons plus neutrons in 131, and this is just protons. So if you just subtract off the number of protons, then you will get 78, and this is just the number of neutrons, okay? Should be Should be 78. Okay. All right, I'm going to skip over this example. There's a typo there. I just forgot to fix it. But let's look at this bottom one. You're going to do the exact same thing now, just with carbon. I have carbon 14. I'm calling it that. That's the isotope name. How many neutrons are in carbon 14? Yep, I'm looking at the chat. You should do. So this is the 14 is the number of neutrons plus protons. 6 is just the number of protons. So if we do 14 minus 6, we'll get the number of neutrons only. And I'm seeing in the chat, that's 8. Okay. Here's another question. So, well, we're going to actually pause all this little calculating for just a second. I want to talk about one more aspect. We have 2 more aspects about isotopes we're going to hit before we're done. The first one is, it's called percent natural abundance. Okay. So because we have different isotopes, for carbon, for example, you can have carbon 12, 13, 14. Here, we're looking at sodium and nitrogen again. So if we have isotopes, if we had all the carbon in the world, for example, if we had 100% of all carbon in the world, well, we would all be dead because we would have to extract the carbon from all of our bodies. But if we had all the carbon in the world, okay, a certain percent would be carbon 12. A certain percent would be carbon 13, and a certain percent would be carbon 14. And if there's any other carbon isotope, those are the main 3 I can think of. But if you add those up, we should get 100% of all the carbon in the world, right? So the percent natural abundance is just how much of that element is a particular isotope. What percent of the entire abundance of that element is a particular isotope, okay? So every isotope has a percent natural abundance. It doesn't make up 100% of that element. It makes up a portion of that element. Does that make sense? So for example, sodium, some elements only have one, they don't have any isotopes. They're just present in one particular amount. So sodium, for example, is all sodium 23. Okay, if you look at the mass here, it's just right near 23. So we call that sodium 23. We round up. And it has no isotopes. Every sodium atom is going to have that mass. Nitrogen, on the other hand, if we look over here, we've got 2 isotopes. All right, and there they are. We've got nitrogen 14 and we've got nitrogen 15. Some atoms of nitrogen, when you add them up, because varying numbers of neutrons, they add up to 14 as their mass number. And then some nitrogen isotopes have one more neutron. Okay, so nitrogen 14 has 7 protons, so it must have 7 neutrons to add up to 14. Nitrogen 15 has 7 protons and it has 8 neutrons to add up to 15. And if you look, here's what I want to talk about. Their percent natural abundances. Most of the nitrogen in the world, 99.64%, is nitrogen 14. Very, very little of the nitrogen in the world is nitrogen 15. Okay, so nitrogen is one of the molecules, one of the main molecules in our atmosphere. You're breathing it in right now. Which of the following nitrogen molecules is the most common molecule in the air in, well, I'll say your room? What do you think? Would it be A, 2 atoms of nitrogen 14 put together, B, an atom of nitrogen 14, atom of nitrogen 15, or C, 2 atoms of nitrogen 15? Based on percent natural abundances, which one's going to be most common? Okay, everybody's saying A. That's right. 99.6% is nitrogen 14. So we're not breathing in any nitrogen 15. It hardly exists. All that nitrogen is nitrogen 14. Okay. All right, last thing for today. Once we get to through atomic weight, this is, I think, the last slide. Yeah. Okay, so atomic weight, that's the last thing with isotopes I want to talk about. It is a weighted average of the atomic masses of all isotopes of that element. Okay, because you have different isotopes, we have to take all those into account. When we report the mass of a particular element, so if you look at the periodic table and you see the mass number under any given element, that is an average. We have accounted for all the isotopes and we've taken the average of their masses, okay, to report the overall mass of a particular element. So to do that, we have to account for the type and then the natural occurrences, which is almost like saying, it's like saying the percent abundance of an element's isotopes. And that is what determines the element's atomic weight overall. It's a weighted average. So for example, let's go back to copper. Remember we had 2 isotopes of copper that we calculated earlier, copper 63 and copper 65. When we report, when we just say them by name, we just use the whole number. We just round up because it takes a lot more time to say copper 62.9396. So we just say copper 63. Usually you can round. It's a very small amount you have to round. But the actual mass of copper 63 is this, 62.9396 AMUs. The actual mass of copper 65 is 64.928 AMUs. Okay. Now, if we're looking at the percent abundances of these 2 isotopes, of all the copper in the world, 69.2% of that copper is this copper 63 isotope. Okay, so that's the one that's more abundant in the natural world. And 30.8% of copper is copper 65. And if you add those 2% up, guess what? You get 100%. Okay. Now, if we want to calculate the atomic weight of copper, we have to account for both isotopes. So here's the way you do it. You are going to take the mass in AMUs of an isotope, and you're going to multiply it by its percent abundance as a decimal. I'm going to say that again. You're going to take the mass and weight of that isotope, and you're going to multiply it by its percent abundance written as a decimal. So let's do that for copper 63. We're going to do 62.9396 AMUs. And we are going to multiply this by the percent written as a decimal. So essentially you're going to take this percent, divide by 100. What do you get? 0.6, oh, that's a 9, 692. So there's this is the mass of copper 63. And we're multiplying it by the percent abundance written as a decimal. And then we have to do it for all the isotopes that are present. So now we're going to do that same thing for copper 65. We're going to add it all up. So for copper 65, here is the mass, 64.928. And we are going to multiply that by the percent written as a decimal. So 0.308. Getting close to the edge. Okay. So this was the mass of copper 65, and that was the percent abundance written as a decimal. And we just multiply those and we add them up. So the atomic weight, when you do that, the averaged atomic weight for copper is 63.55. And if you look at any periodic table, that's what you see. Okay. And they've done that for literally every element. Okay. So if I ask you to calculate, if I gave you the isotopes of a particular element, I said, here's their percent abundances, here's their AMUs, could you calculate an atomic weight like this? Okay. Well, that is it for today. It's as far as I wanted to get. And I wanted to launch one last little review poll. So this is a no thinking question. I just want to know, I've been meaning to do this after almost every lecture. I just run out of time sometimes. How much of today's material do you think you fully comprehended? Be honest with me. Okay, now I know there's different variables at play. Some of you have a lot going on around you, people coming in and out of your room, maybe your phone's been ringing. Okay, so some of it might be due to distractions on your end. Some of it might be you just didn't fully understand something I said, or you think you felt like I rushed through something. Most everybody has voted now, so I'm going to end the poll, share the results. So most everybody said that they got about 75%. But there's a couple of people, and those are the people I want to talk to you real quick. If you feel like you only got half of this material or less, I want to ask, why is that? Is it you felt like I rushed through something? Are there distractions on your end? Is this stuff just brand new to you? Okay, there could be many, many reasons. So if you feel like you got half of this material or less, you need to reach out to me. Send me an email. Let's set up a Zoom. Ask me your questions. Let's go over something. Remember that I want you to be doing the required reading as well. You should have read sections 2.2, or sorry, 2.1, 2.2, and 2.3 for this lecture in the textbook, okay? And I take that seriously. I had students who really also took that seriously last semester in the fall, and they did very well. And they communicated to me that reading the textbook helped, okay? So please take that seriously. And if you're wondering, how can I do better? I just don't feel like I'm doing great. Join me on my office hour. I'm about to start an office hour at 9:30. I have a student that I'm expecting to join because they've asked some questions. We're going to talk through some stuff. I'm looking forward to it. And if there's any other questions you have, let me know. But that puts us at our time for today. I will see you guys next Tuesday, and you'll have quiz 2 next Tuesday as well. Y'all have a good weekend. If there's any questions, I'll stick around.